So now we're ready to start the next method that you may need to employ sometimes just because of the region and the spinning that you're doing with this volume. So we're going to move into the washer method, and I'll show you how that's happening. And what I'm going to do is set this up. Obviously you can kind of see that I've already drawn the image and shaded it out, and then we'll put our spinner in. So we're going to find the volume of the solid obtained by rotating the region. That's really important. I want to identify that first. In the first quadrant, bounded by y equals x squared, the x-axis, and the line x equals 2. So that is your region. That's what you want to really spend a lot of time on. You don't want to go too fast and be worried about where you're spinning. You want to identify your region, which is already drawn in for you. Here's y equals x squared, here's x equals 2, there's my x-axis. So very similar region that we discussed in the last video. However, when I see that word about, I really see like this other color in my brain, like, okay, now is where I'm talking about where I'm spinning. I'm going to spin along the y-axis. Notice that this spinner is not one of your boundary lines. That's an important thing. That's different. So I'm gonna bold it out. I like to like really make it obnoxious. Here's where I'm spinning. And so that's why you kind of see the mirror image here on the left-hand side. What am I actually creating? Well, you're creating sort of this really weird cylindrical looking shape, right? But it's kind of hollowed out in the middle, right? On the outside, it would look like a regular old cylinder, but almost like maybe a vase or something is like dug out in the center. So this causes an issue here. I'm going to try to keep the same structure of the disc method, and let's revisit what that was saying. I'm going to call it a washer for a particular reason. There's going to be an issue here. If I draw my rectangle perpendicular to the axis of rotation, so I'm going to put this, draw a rectangle perpendicular to the axis of rotation. I will do that. And let me add in here and make sure that you draw it perpendicular to the axis of rotation in the shaded region. In the shaded region. Notice how I only drew it in that shaded region. I didn't connect it to the axis of rotation. It's in that shaded region. I'm going to bold that so we can really see it. What you notice here is that rectangle is no longer touching the axis of rotation. You have this big gap in the middle. And that's how you know that this is a washer method. So I'm going to add to my description over here. We drew a rectangle, it was perpendicular to the axis of rotation in the shaded region. That's all the same stuff we said for disc method. But it's not touching the axis of rotation. You've got a gap in the middle. When it's not touching the axis of rotation, that is a washer method, because if you actually imagine that rectangle, and you can kind of see it horizontally presented here, if you imagine spinning that around the y-axis, what you actually create is, yes, you create a washer, kind of like a donut. Okay, it's got this kind of hollowed out section there. So you create a donut kind of structure here. And so I'm going to try to redraw that so that we can really see what's going on here. I'm going to do the same thing that we did to develop the disc method. I'm not going to ask you to prove this. I just want you to know where this formula is coming from. And how do you know disc versus washer? Disc, your rectangle is touching the axis of rotation. But in a washer method, your rectangle is not touching the axis of rotation. So I'm going to do my best to draw this washer that we had just created. And so I'm going to do that. See, if it was touching, you would create a disc. But what I have going on here is I've got this like kind of gap in the middle. There's my axis of rotation, kind of piercing through my image. So it's very similar to disc in the sense of like, well, you start out with a cylinder, you just have a hole in the middle. That's pretty much what we're going to do to describe the volume here, right? So I would like to talk about this and say, okay, how would I go about finding the volume of this solid. And we're going to sort of take the same approach. Like, let's imagine, what if I just tried to find the volume of this one donut, this one little washer? What would the volume of this one washer be? Well, it pretty much is a cylinder, right? You would basically say, well, let's do the volume of the outside cylinder, and then let's subtract off the volume of the inside cylinder. That's pretty much our strategy here, basic geometry stuff. So let's kind of jump around here and go right to our geometry, and let's mark up our picture. We basically have, you know, in this donut structure, the outside cylinder, I'll mark that up, has a radius to the outside, the furthest away point. I'm going to call that cap R. So the volume of that outer cylinder is this larger, larger radius. Now remember, a cylinder has a volume of pi r squared. Now again, I have this like dimension over here that's h, so I'm going to throw that in. Now you have this inside cylinder, which is smaller, so it has a shorter radius, and I'm going to mark that up as such right here to that inside part. That's what r, your little r is. It's a different sized radius. So what I'm going to do is use that and say, well, what I'm going to do is subtract pi little r squared times h. That would be the volume of that one sort of concrete washer. What I'm going to do is go through the motions. If I really wanted to approach this volume as like a Riemann sum approach, then I could certainly do that. I could say, you know, my total volume I could approximate by saying, hey, let's add up a bunch of these volumes of washers. But I don't want to do an approximation. I want to get exactly to it. So what I actually want to do is I'm just going to kind of squeak this in here. Well, I guess I'll go like this. I'll just do, well, it could equal, what if I were to take that h and make it get really, really small, close to 0, up against that sigma? Whenever you see that happen, that's where your problem changes into a definite integral. And so that's where we're going to get our formula for the washer method. So our volume by the washer method I'm going to generate in two different ways. Now, what you can notice about this is that limit up against the sigma turns it into an integral. Like right here, those combine and say, there's my integral. Now what I'm going to do is kind of a fancy situation of factoring here. Do you notice in the step above, each one of those guys has a pi? You saw that in disk method. I'm going to factor it out. I'm actually going to move it outside the integral. Now the meat inside the integral here is I have cap r squared minus little r squared. Now notice I left off the h. That's because I'm going to kind of factor that out as well, kind of like outside the structure. But let's actually think about what h really is. Let's go back up to our image and think about what h is. H here is drawn in this particular way, which is the orientation we have here. So here's h on my geometric presentation of what that washer is. And if I slide back to this image, here's h. H is actually some really small change in y variable, in the y value. So that means if I drew this rectangle perpendicular to the axis of rotation, and it has a horizontal format, I've got a delta y situation, which is going to translate in my integral to a dy. So I'm going to come back here and say, for this problem, you know, instead of saying h, I'm going to instead say dy. Now I did that because my rectangle in the shaded region was a horizontal presentation. Obviously, I can switch around and say, well, what if I had a vertical presentation? The meat of your integral would be the same, but you would have a dx presentation of that integral. So again, this is what I want you to know as far as like, hey, what's the formula for the volume by Washer method? You have two ways, whatever it presents itself. Perpendicular could look horizontal, as in this case, or it could look vertical. So I just wanted to give you some background. So like, where does this crazy formula come from? It comes from basic old school geometry. So I'm going to fly around again. I'm not going to ask you to prove that, but I will ask you to execute this problem. So let's go back to our picture and say, okay, well, here's my problem. Let's actually address it. And I have everything drawn in really nicely. Let's address what's going on. Let's see if I can erase the individual lines that I want to go away to not junk up my picture terribly. Can get rid of that one. There we go. Actually, I'll get rid of this stuff too. Okay, so there's my rectangle that is drawn perpendicular to the axis of rotation. It's in the shaded region, but it is not touching the axis of rotation. So let me just kind of bold that out so we can see it. What I want you to do is let's think about what cap r and little r is. I'm going to draw it here. I'm going to write down what's cap r. Cap r is the distance from the outermost point to the axis of rotation. And little r, well, is the distance from the innermost point to the axis of rotation. And when I say inner point and outer point, I mean of the rectangle that you just drew in, right? So if I go back to my picture and say, okay, let's figure it out. Cap r is the furthest away point, this guy over here. How far is that point to my axis of rotation? That is cap r. Now let's think about it. That ordered pair on that outermost point, no matter what, the x-coordinate is 2. But I don't know what the y-coordinate is, right? There's no magic to where you draw that horizontal rectangle. So the y-coordinate could be anything, but the x-coordinate is 2. It's fixed on that line. That's one of your boundaries. Okay, so if I need to describe in this situation what r is, no matter where I draw it, it doesn't matter. It's going to be the difference in x-coordinates, right? Because in this case, it's going to be the right endpoint minus the left endpoint, this distance from this value to that value. So in this case, my r value, I'll just change color so I'm actually making a decision for this problem, is actually 2 minus 0. You're basically doing right minus left. That's your outer radius. Now, your inner r is the distance from the innermost point on that rectangle. So here it is, to the axis of rotation. That's your distance for little r. How far away is that? Now that is variable because that ordered pair right there, well, that's any ordered pair x comma y. X is variable and y is variable. I don't know what that ordered pair is. So in order to describe, like, well, how long is that inner radius? It varies. And it really is, it's still right minus left. It's still a difference in x coordinate. So this one is variable, meaning there's a variable in it. It's x minus 0. There's my scenario. Okay. So I'm going to set this up. Let's think about this. We're doing this via the Washer method. I've got my rectangle drawn in perfectly. It is drawn horizontally, which in this case tells me a couple of things. My volume, so I can get going and say, I'm going to write my answer here. I got something good happening. My volume is going to have a pi on the outside. It's going to be cap r squared minus little r squared, and it's dy because I saw that horizontal presentation. I can go back to my imagery and find my limits of integration, right? Because if you draw that rectangle as low as it could go, it would be at y equals 0. And then you keep drawing all these rectangles in the horizontal format until you get to that endpoint, which happens to be when x is 2, y is 4. So those are my limits of integration, 0 to 4. They're coming from the y-axis. But what this integral also tells me, that dy says, hey, everything inside this integral has to be a y variable. I can't leave, I mean, the r, cap r being 2 is totally fine. I can just say equals 2, right? But this little r cannot remain as x minus 0. It's got to be in terms of y. So let's go back to our work here and say, well, I know what the equation is. It's y equals x squared. Well, that means I have to, again, algebraically solve and say, well, that means the square root of y equals x. We did that in the last video. And so you just need to do it whenever appropriate. If this is a dy integral, you need to get rid of that x and replace it with its substitution, which is square root of y. And again, I don't need to write the minus 0 because, you know, not necessary. So look, this wouldn't earn you, credit for setting up the volume of, setting up the integral that represents the volume. You need to actually plug the pieces in. Cap r is 2, and little r is square root of y. Now this would earn you full credit because that is ready to go. Right? Now notice that cap r and little r are squared individually, right? So it's certainly worth it to do that work. 2 squared is 4. Square root of y squared is y. And again, this is not a terrifying integral to have to evaluate by hand. It's pretty nice, actually. So I can actually crunch the numbers. And the way this was phrased, it definitely said, find the volume of the solid. So I will do that. My antiderivative, I'll leave the pi in. My antiderivative is 4y minus 1/2 y squared. I'm going to evaluate that at 4 and 0. That would be 16 minus 8, and then a bunch of zeros. So my volume here is 8 pi. Okay. So you do not have to prove the washer method. I just wanted to give you some background onto where it came from, so hopefully it makes a little more sense to you. But this is what your washer method looks like. Okay, so very similar to this, to the disk method. You're going to draw your rectangle perpendicular. If your rectangle is touching the axis of rotation the whole time, then you're in disk method. If you're not touching the axis of rotation the whole time, that's how you know you're in washer method. Okay, so let's do 2 more examples of these so that we can sort of get our handle on practicing them. Now again, you're going to be responsible to draw these images. And I don't think that these are terrifying because these are some of your common functions you learned in pre-calculus or advanced algebra, the square root of x function. So here I have the square root of x function. It's this one right here. And of course we have y equals x squared that you know. I'll just change the color just to make it something different. That's this guy. So nice to mark up your picture. So we're going to find the volume of the solid obtained by rotating this region bounded by the square root of x and y equals x squared. Here's my region R that is shaded, right? And right when you see that word about, you sort of take a break and like make sure, do I have my region set up? Do I have everything shaded in? Now you, separately from that, now you care about where you're spinning. So I've got my region shaded. I'm going to revolve this thing about the x-axis. So I'm going to bold the x-axis so I can see it. So it's really obnoxious there. Now, I am going to do the best I can. I'm going to draw a rectangle in the shaded region perpendicular to the axis of rotation. That's what I'm going to do. Notice how I'm only staying in the shaded region. And this is what perpendicular to the axis of rotation looks like. What you can clearly see is you have a gap here. This is not touching the axis of rotation consistently through this interval. So that's how you know, okay, I'm in the washer method. I will get set up that way and I'll make it work. So here's my rectangle. Now, these 2 ordered pairs are like any, random ordered pair. There's nothing special about where I drew them. It's just that this top function is the square root function and this bottom function is the parabola. So this is definitely, I'm going to label this. This is a washer method because your rectangle is not touching the axis of rotation. Now, I'm going to describe what these capital R and little r look like. You know a lot of information right now. What you know is your volume is going to have a pi on the outside of your integral. It's going to be cap r squared minus little r squared. And you know that this integral is dx. You have a vertical presentation on that rectangle. You could actually just kind of think about your limits of integration right now if you want to. They are not described in this problem. You have to go fishing and find them, which means let's actually set these two functions equal to each other so that I can find my intersection points, right? So if I set them equal to each other, what do I have? Well, I'll square both sides to get rid of that. Let's get rid of that radical. And then I'll move all the terms over to one side of the equation. Now what does that give me? I'm going to factor. And that gives me two answers here. X equals 0 and x equals 1. And you might have been able to figure that out just from reasonably, guess and check in your head. But this literally is the intersection point of 1. And here's 0. I can fill that in my integral now. But I'd like to mark up my picture with what exactly is cap r and what exactly is little r. So I will do that. Here's cap r. It's the distance from the outermost point to the axis of rotation. So cap r is going to be that top y equation minus 0. Okay, because that's your axis of rotation. The x-axis is y equals 0. So it's whatever this y coordinate is minus the y coordinate of 0. Now, I already know my integral is supposed to be in the x variable, right? So let's switch this over right away. That top y is off that equation of the square root of x. I'm going to do that right away. And then the little r is that distance from the innermost point to the axis of rotation. Maybe this is a good color. I don't know. Maybe not. But it's this distance in here. That's little r. Maybe that's not a great color. So again, that's still a difference in y coordinates. It's still y minus 0. So little r, kind of move over here, is still y minus 0. But let's switch it around. I have to have it in terms of x because the integral tells me so. But the y value that we're referring to here is y equals x squared. That's the ordered pair it's coming from. So let me move over and let me actually set up my volume here and put all of the pieces in play here. Cap r is really the square root of x minus 0. I can just leave it square root of x. Little r is x squared. I don't have to write the minus 0. But notice how they're individually squared. Be really careful that you don't do something terribly wrong algebraically. And by that I mean, I don't want you to do quantity squared. This is a huge mistake in the Washer method. So do your absolute best not to do this. This is really, really bad. I'm going to put a line through it. Notice that your cap r and your little r are individually squared. So this is the integral that would represent the volume of this solid. They actually asked me to find the volume, so it would be my responsibility to solve this all the way out. Okay. Which I believe you can all do, but let's just walk through the antiderivative and we'll get there. So I'm going to leave the pi. Let's see, that's going to be 1/2 x squared minus 1/5 x to the 5th. I'm going to plug in a 1 and a 0. So what do I end up with? 1/2 minus 1/5, and then, well, 0. So what's 1/2 minus 1/5? Well, that's going to be, do a common denominator of 10. That would be 5/10 minus 2/10, which is 3/10. So 3/10 pi, or 3 pi over 10. Okay. And let's come back to our other region here. This is our last example of a Washer method, and let's discuss why it's a Washer method. In this case, I've got the volume of the solid. I'm going to find the volume of the solid obtained by rotating the region bounded by y equals the square root of sine x. That's what's shown in your picture. And the x-axis, so same region that we had discussed before, from 0 to pi, right? 0 and pi, there it is. So no fishing for those limits of integration. When we're rotating at about y equals -1. So here is your horizontal line. It's underneath the x-axis. That's our rotation. That's important. So I've got my shaded region already set up. And remember, separate from that is where you think about, well, where do I care about rotating? It's right after that word about where you're going to say, okay, let me bold that line, this horizontal line below the x-axis. This is my spinner. Now, let's discuss why this particular problem is in this video for the washer method, because you're going to draw your rectangle in perpendicular to your axis of rotation. There is nothing special about where you draw it. It just has to be in the shaded region. Notice I'm not connecting it to my axis of rotation. You draw that rectangle in the shaded region, and I'm going to outline it here. There's nothing special about where you draw it, but if you realize that that rectangle is not touching the axis of rotation, that you have this like extra space in the middle, well then now you know you're in the washer method. So when you see that gap, that's a washer presentation. So let's sort of mark up my picture. And you can do this in any order that you want to, of course, right? The outermost point to the axis of rotation, that's cap R. And again, this is any random XY ordered pair that could occur. There's nothing special about where I drew it. So that cap R is top minus bottom. Now notice what's happening here. It's that Y coordinate, whatever it is, minus this Y coordinate of -1. So your cap R is Y plus 1. I'm going to leave it like that for now. Okay. My little r, let's go in and grab that one, is the innermost point to the axis of rotation. Now let's talk about that ordered pair down here. Now this one has any x coordinate. I'm not quite sure where to draw. It's variable, right? But your y coordinate is 0. You're on the x-axis. That's part of your boundary of that region. So when I want to talk about the length of little r here, it's really 0 minus -1. Okay, so again, imagining what you're creating this weird, kind of like a bead almost. You're taking this thing and spinning it around y equals -1. You've got this hollowed out center, but you've got this cylindrical kind of curvy shape around the edge. I kind of view it as like a bead to make a necklace. Okay, but this is washer method, so let's think about it. We drew our rectangle in a vertical presentation, which means I know a lot about the setup of this integral, that it's going to be cap r squared minus little r squared dx. That drives what I'm doing. That means I get my limits of integration from the x-axis. So again, imagine that rectangle sliding all the way to the left. That would be x equals 0. And then you build those rectangles all the way out until you get to x equals pi. Cap r, I'll just throw it in and we'll see how weird it looks, right? Cap r, I said, is y plus 1. Well, that looks weird. Little r is just 1. Now again, you're individually squaring these, but this is totally weird because I can't have y inside an integral that's dx. Like, that's just strange. So I have to get rid of it, and get rid of it legally. Now remember, you have a substitution for y. It's the square root of the sine x plus 1. Okay. And I could just say 1 squared is 1. Now look, this is a class that is a no calculator class. We do not have the skills to actually evaluate this integral by hand. And so I'm going to stop here. You cannot evaluate this by hand. So instead of saying find the volume, I'm going to change the directions here and say, well, what would it look like? It would look like this. It would say, hey, set up the integral that represents the volume of the solid. That's what you're going to see. And so this is an integral that is set up wonderfully well. I have good parentheses, good communication, but it is impossible to evaluate this integral without the use of technology, whether it be a graphing calculator or a computer. So we are going to stop here. And that's what you would see the directions look like. Okay, so in our notes that you see posted, I have a couple of extra problems which would be great for you to try. I will post an answer key to those. And of course, if you have questions with any of those, that would be what office hours is for, and I can certainly talk them out. But you can kind of see here is where I started using that language of, hey, set up an integral expression that represents the volume. That means you don't necessarily have to evaluate the integral. I'm just looking for the setup. And in this case, I want you to do both. I want to give you a lot of opportunities to show that you know how to do volumes. And you're going to have to evaluate some of them to find the volume, but I'm more interested in getting you to do as many setups as possible. That's a really important application of the integral. So I will post up the answer key to both problem 6 and 7 so that you can kind of use what you learned in this class and sort of in this video lesson and check your work. Okay, so thank you very much.